And so we said this first part here is like 16 years of research and preclinical testing and clinical testing, and then you finally send all your data to the government, and then they take 2 more years to decide if they want to approve your drug. Okay. Protein kinases, okay? These are enzymes that transfer the terminal phosphate of ATP onto a hydroxyl group of one of 3 different types of side groups, serine, threonine, or tyrosine, on a protein. Okay? You have a protein, it has one of these 3 residues with a hydroxyl group. Protein kinase comes in, takes the phosphate off of ATP, puts it onto the protein. This half of the cycle we don't talk about. Okay. Abl kinase is a particular kinase. It happens to only phosphorylate tyrosine residues. Again, I don't care if you memorize specific details of any of these things, more of a broader understanding of how this is working, as opposed to, I remember that it's called Abl kinase. It's a tyrosine kinase. I don't care about that. Okay? But Abl kinase has involvement in transmission, signaling transmission between cells. And so if it's turned on sort of continuously, especially in white blood cells, they will start to proliferate and grow out of control, leading to a particular type of leukemia. Okay, and so we said imatinib or Gleevec. Actually deleted all the slides that have more drug names on them. Some fun times in the past 2 semesters were me trying to read the drug names because they're so ridiculously unpronounceable. But I cut all the extra examples. So I think there's like maybe 1 slide that has a bunch of drug names on it I could try to read. So Abl kinase inhibitor is a treatment for CML. So it binds to Abl kinase so that Abl kinase cannot function. It can't bind ATP. It can't phosphorylate other things. Okay. And then we answered this last time. So usual drug approval times are a couple years, but Gleevec holds the record for the fastest drug ever approved. The next closest is like 6 months. Okay. So like I said, this is how it works. Here's Abl kinase. It binds ATP. It puts ATP onto some other protein. In this case, it can put it onto a cancerous protein and sort of lead to this out-of-control growth. But if Gleevec comes in and blocks this site, then you're not going to phosphorylate any cancerous proteins, and you prevent the progression of the disease. Okay. So here begin slides you haven't seen before. Okay? So the function of Abl kinase requires the binding of ATP to its binding site. And what imatinib does is it inhibits Abl from doing that by blocking the ATP binding site with the drug. The drug is in that site instead. And so what we have in this figure here is this is the actual sort of structure of the binding site. And here's what ATP looks like when it's binding in there. So there's sort of a hydrophobic side, a polar side. We have 3 different hydrogen bonds involved in ATP binding into this site. And so when we're trying to identify a lead compound or sort of a scaffold for our initial drug, we want something that looks kind of similar. So we are going to pick something that has sort of a hydrophobic area, polar area. We've decided 2 H bonds is good enough for us in this case. Okay. And then these R groups here represent sort of 3 different functional groups that we could tweak. We'll put different groups on there and see how the affinity for the binding site in Abl kinase is for our different drugs. Okay. So the lead compound is mimicking the hydrogen bonds. It sort of forms our initial drug scaffold, and then I said there's at least 3 different positions that we'll sort of modify with some different chemistry, and we'll run a bunch of binding assays and see how our drug is interacting with the Abl kinase. So here is sort of the initial drug scaffold. In this case, we've added sort of like a nitrogen benzene looking ring, and these are some fluorines. I don't know what this group is, but we've put a couple. We just have an H in the R2 site, so we put a couple of different groups on, and we've looked at relative binding affinity. This relative binding affinity is relative to the final KD of imatinib. So the final dissociation constant for Gleevec is 10 nanomolar. Okay, and so this is about 1,000 times worse than that, or in the micromolar range. So then they tried some different groups. Look at it, it's, I don't know, about the same. Okay, now it's only 100 times worse. Okay, let's go back to our fluorine, try something different here. Sadly, this is sometimes how it really happens. Just try some different chemistry and see what we get. This is maybe 10 times worse. And then finally, we come up with our final drug structure. And it has a nice, super high affinity for us. Okay? So like I said, competitive inhibition is when you have a molecule that is blocking the function of a protein by displacing the naturally occurring ligand. Okay? And binding of both would be mutually incompatible. They can't both bind to the exact same binding pocket, so it's one or the other. So based on this definition and what we just saw in the other slides, is Gleevec a competitive inhibitor? Yes, it takes the place of where ATP needs to bind. Many drugs, most drugs, a lot of drugs are designed to be this way, with the goal being maximize affinity so the drug can actually compete off the naturally occurring ligand, maximize specificity so you prevent side effects. And like I said, these are a trade-off. This is a real thing. What if you are somebody who has resistance to Gleevec because you have some sort of mutations in your Abl kinase? So this drug doesn't work for you. Now what kind of drug do I need to make for you? Any ideas? That's the answer. An allosteric drug, okay? So something that is non-competitive, right? So this is just I'm binding again in some other site such that the naturally occurring ligand isn't going to be able to bind anyway. And generally when this happens, you bind some other site and it changes the way the binding pocket is oriented so that the drug can't get in or fit or whatever it needs. Okay. There's a section in the book, I can't remember what section it is, of chapter 12 on apparent affinity, and it has some curves for sort of the half maximum concentration you need for an inhibitor. I'm not going to ask any questions about that, so if you are reading through and come across that, none of the apparent affinity or like IC50 curves we won't talk about. Okay. So we said to raise affinity, you raise hydrophobicity. Hydrophobic interactions are sort of non-specific. Any two hydrophobic things could have some hydrophobic interactions going on. But when you start actually using some positive and negatively charged residues, those have much more specific types of interactions. And so you sort of need to find a sweet spot between the number of hydrophobic residues in your binding site and the number of sort of polar or charged residues.